Hello guys, welcome to my channel. And so today let's see about radar receivers. So in radar receivers, what is the functionality of it? So basically, what a radar receiver do is it will receive an weak echo signal from the target, and it will amplify it to such a level that it can be displayed on the screen. So to monitor or to do like in further processing, there are few other steps what and all it will do. We can see in the further slides. Okay, so it employs a matched filter. And so what are the things that can be present in the radar receiver is like a matched filter will be there. So what it will do, it will maximize the peak signal. So it is a very weak echo signal, so we should amplify it. So they are using a matched filter to do that. So up to which it will maximize peak signal to mean noise ratio and discriminate against unwanted signals whose waveforms are different from those transmitted by the radar. So and also it will filters out the unwanted signal that is being received. So next it separates. It also can identify moving targets and also stationary targets by using Doppler frequency shift. Okay, so the Doppler frequency shift and all we can see in the next chapters. So next it performs the target detection process automatically based on the threshold set. So basically if an echo received from one target will be different from the other targets. So by that process it can identify whether this was the required target or it was not. So it can identify that. And also it extracts detection. So it extracts detection in addition to the information about the target location and range angle. Not only identifying the target, also gives the angle and the range at which the target is located. It acquires targets and tracking automatically, and only process tracks are displayed to the radar operator as to send some automatic device such as an air traffic control system or weapon control computer for further use. So it also tracks the path of the targeted object. So by which they can see which path or which trace it will take. Next, so constant false alarm rate. So you also already from the previous videos you might think you might got what is a false alarm. So using this constant false alarm rate, it will reduce the false detection and thus avoiding the overload to the tracker. So basically using the probability of false alarm by using the timings, average time and all. So using that model they will predict whether or they can reduce the probability of false detection. So actually, the target will the tracker no need to have that much load, because anyways we are already monitoring the time gap between the false alarms. So by which we can automatically change, or we can automatically decide whether it is a false detection or not. So next, in addition to the above, radar receiver performs the following. So what it can do, it will signal processing, information extraction, data processing, electromagnetic compatibility, and electronic counter and countermeasures. So this is electronic counter and countermeasures will be abbreviated as ECCM. Next, receiver noise figure. So noise figure is also known as FN. So this was also already studied or told in the previous class. So noise figure can be termed as if you want the derivation or definition, you can see in the previous classes also. So this is defined as the measure of the noise produced by the practical receiver compared to the noise of an ideal receiver. So you can see why it is like noise of an ideal receiver. Actually I explained there. Ideal receiver in the sense the environment is noise, still even the environment is noiseless or noise free, there will be noise generated by the electronically moving parts of a receiver. Okay, so Fn is equals to N naught by KT N naught KT naught BNG. This is the formula that we got Fn for Fn, and by substituting for n in and all, we can just replace the terms. We will get s in by n in by s out by n out. So s in is signal input and noise input, signal output, noise output. So we can have n out is the available output noise power, n in is kt naught beta bn, kt naught bn, where k is the Boltzmann constant, t naught is the standard room temperature in Kelvin, that is 290 Kelvin, and bn is the noise bandwidth, g is the available gain, or s out by s in. S out is available output signal power and S in is the available input signal power. Now coming to this equation, the noise figure can be interrupted at the decreasing or degradation of the SNR as the signal passes through the receiver. Actually, you know, when we send a signal through a receiver, when the signal progresses to each of the block, the signal will get diminished. So the noise figure may also be into the pattern as the ratio of the noise power out of the actual network to the noise power out of an ideal network. So that amplifies the input thermal noise and introduces the n0 additional noise to its own. Therefore, can be expressed as this. So basically, while it progresses through the network, there will be another additional noise can be added, that can be termed as like this. So kt naught bng plus del n by kt naught bng. Okay. So because that n out can be written as this way. Okay. After writing this, when you calculate or simplify it, this term get cancel and 1 plus delta n by kt naught bn. So delta n is the additional noise introduced by the practical network. So now what happens if we cascade these networks? So when suppose let us take two networks, one has a noise figure as f1, gain as g1 and bandwidth as bn, and b2 g2 bn. So both of the networks have the same noise bandwidth. So just the variation is in noise figure and the gain. So when you try to combine in cascade, the resultant noise figure can be written as f0. So total gain, we know that the systems in the cascade, so gains will be multiplied, so g1 g2, and output is n0. So from this, when you derive, we will get an equation like this: f0 is equals to f1 plus f2 minus 1 by g1. So this is for only two networks are in cascade. If for example there are n networks, the formula will be become like this. Okay. So anything is so from the equation it is clear that it is not sufficient to have low noise figure. The second stage must also have a low noise figure. Okay. So for the n networks present, so this is a three network cascade. So the formula is like f1 plus f2 minus 1 by g1 plus f2 minus 1 by g1 g2. So when you observe, there is no need of gain, or for example so there, when you observe in the first equation or the first case, here no need of any the g2, that means gain of the second network. Okay, we are not using in the formula. So without knowing what is the gain of the second network also, we can find total f0. In the same way for the third also, here g3, it is g3, so no need of g3 to find f0. Just we need f3 and all. So from that we can write a generalized equation for n networks in cascade can be f0 is equals to f1 plus f2 minus 1 by g1 plus f3 minus 1 by g1 g2 plus so on, fn minus 1 by g1 g2 g3 gn minus 1. This is how we can write. And the problem here is so when you are trying to substitute the noise figure and all, you should substitute normal values, not the dB. If they are given in the dB, we need to convert into normal value and then substitute this. Okay, so it is 3 dB, so that's why the 10 power point. So because 10 log x is equals to 3 dB here. Okay, from that we need to substitute do 10 log of f1 is equal to 3 dB. What is the f1 like that? So this is our three networks, same. So now, so here also you can observe that without knowing the third or f3 or g3, we don't know, but still we are able to find what is the total, because they gave us total f0. From that only we can directly find f3 from the above equation. You substitute and we will get f3. Noise temperature. So basically in general, that noise can be caused due to noise most often. So the noise introduced by network may also be expressed as the effective noise temperature, that is TE. So effective noise temperature TE is defined as the temperature at input of the network that accounts for the additional noise delta n at the output. So T is according to the input, okay, temperature at the input that accounts in the additional noise that causes that additional noise to occur at the output. Basically the effective temperature, the noise temperature that is present in the input that causes output the delta n noise at the output. So to find, like when you write the equation, when is do this f1 and we just this delta n is what we know T. So KTA BNG by KT not BN G. So where delta n is the KTA BNG. So instead of T naught, that is room temperature, we are substituting what is the temperature at that present scenario or that at that moment. So after calculating, we got T is equals to Fn minus 1 of T naught. So now coming to the cascade of the network, so similar way we'll get an expression like T is equals to T1 plus Te2 by G1. So when it comes to n networks in cascade, or effective noise temperature of a n network cascade will be T is equals to Te1 plus Te2 by G1 plus Te3 by G1 G2 plus so on Ten by G1 G2 so on Gn. Now consider two networks in cascade with overall effective temperature. They are given. Calculate the sum. So they have given Te1 as this one, overall as 300. They want to find the Te2. G1 also given. So substitute, you will get. Now super heterodyne receiver. So this diagram is seen a lot of times by now. So above there will be a transmitter. Now this is the receiver part. Okay. So in the receiver part, we can see there is first a low noise RF amplifier. Okay, basically a noise amplifier, you can say low noise amplifier also you can say, and low noise amplifier, RF amplifier, that will go to the mixer which is connected to a local oscillator. That output will be sent to the IF amplifier, that is intermediate frequency amplifier, then to a matched filter. Then this resultant pulse will be going to the second detector or 2D detector or demodulator. Now this will be sent to a video amplifier. So in this video amplifier, what depends on the signal that is come from the demodulator, the image will be shown on the display. So basically there are different types of displays and we can see what are those in the further session continuation. Okay, next then it will goes to threshold decision and output. Now coming to, so basically in this video amplifier, this will what will do, it will convert the signal to a proper way so that it can be displayed on the screen. That will it will do. Okay, we can't see a video here. After this output we will see. So next, low noise RF, like let us discuss about each block. First is a low noise RF amplifier. It is the first stage of a super heterodyne receiver for a radar application. It can be transistor amplifier. It can be a transistor amplifier. Next, coming to the mixer, it is used to convert incoming radio frequency signal to intermediate frequency, so as to make the process easier and to make information extraction simple. So okay, so that's why we are adding some signal or adding or subtracting some frequency. So conversion of RF frequency to IF frequency is called down conversion. So this process of conversion from RF to IF is called down conversion. Now noise figure of a mixer used in front end. So we need to check for the noise figure of that mixer. So the noise figure of a mixer is determined by its conversion loss and the noise temperature ratio. So the conversion loss of a mixer is defined as, conversion loss is denoted as LC. So LC can be defined as the ratio of available RF power by available IF power. So LC is the measure of effective efficiency of a mixer in converting RF signal power into IF. So I am giving this much RF signal input and I am getting IF power. So how much efficiently it is, like whether the entire signal is getting converted or a part of the signal is getting converted. So to know the value of that. Now coming to the noise power temperature ratio of a mixer is defined as, okay, noise temperature ratio, that is TR, okay, T for temperature, R for ratio, TR. So that is like actual available IF noise power by available noise power from an equivalent resistance. Okay, so that is termed as like this. Then so we got it, Fm by Lc. So here actually it should be an Fn, but this is a mixer, we are doing for a mixer, so we are out like Fm. So Fm is the mixer noise figure, Lc is the conversion loss, that is also equivalent to 1 by Gc, okay, 1 by Gc, and loss and gain, basically Gc is the gain of converter. Now Lc is the available RF by available IF power. Now coming to Fm is not a complete measure of sensitivity of a receiver with a mixer front end. The overall noise figure depends both on the mixer and IF amplifier. So what we'll do, we just know if the frequency here, noise figure, because these two networks are in cascade, and once the mixers noise figure is Fm, that can be let us consider it as F1, that is LC into TR. Remember this, LC into TR, and IF for IF it is FIF, some frequency, some noise figure corresponding to intermediate frequency. So the net will be FR, noise figure of receiver. So after calculating what we got, FR is equals to LC into TR plus FIF minus 1. Just substitute this values here, that's okay. And this G1 will be corresponds to Gc, so mixers conversion gain basically. So Gc, that gain we have written as here 1 by Gc, you know this LC, right? So just substitute here as LC here, that's it. So problem we can do, say you should convert the dB values to normal values. Okay, now coming to an ideal mixer is one of the whose. Okay, let's see what will happen in the, like what is the use of your local oscillator and all. So an ideal mixer is one whose output is proportional to the product of RF echo signal and the local oscillator LO signal. So this intermediate frequency can be obtained basically in two ways. Either we have to sum that local oscillator frequency with RF frequency, or differ the RF frequency with local oscillator frequency. But as the frequency is lower and on higher frequency, say require okay. So what we'll do, we just take only the like filter will only allows low frequency like a low pass filter. It will only allows the low frequency component, and what will it so the difference, so because FRF plus FLO will be higher somewhere, and now this low frequency only allows that FRF minus FLO. So that what we got at the IF filter. So now dynamic range. So dynamic range is defined as the ratio between maximum input signal power and the minimum input signal power. So basically received by handle without any degradation in the performance. So like the maximum signal that can be input signal. So Smin by Smax by Smin. That means the receiver, the maximum signal power that can be received without any degradation in the performance by the minimum signal that can be detected by that receiver without any degradation in the performance, both of the ratios. So now coming to the noises. So another noise, like in the previously we discussed about temperature noise, like noise related to temperature. Now coming to the flicker noise, that can be also called as 1/f noise. So basically, you can see 1/f noise. That means as the frequency increases, the noise caused or the noise noticed is very less. So when the signal's frequency is too low, we can clearly identify the noise. Basically, it will affect. There will be more noise. So this can be also observed during when you observe some sine wave in a DSO. You can see there is like a low frequency signal. While at low frequency, observe a sine wave in a DSO. You can see it is not like perfect sine. It will be like a zigzag kind. That wave will be like some noise component will also be there. When you increase the frequency, we can't notice that. So it will be like a it will be rapidly changing from +1 to -1, +1 to -1, like that. So we can't observe that noise. So that's what is called a flicker noise or 1/f noise. So this is why it is occurring. It will occur due to semiconductors such as diodes and transistors that are present in the circuit. So the 1/f noise is not important for a radar receiver whose IF frequencies are greater than few hundred kilohertz. This is in this case most radar IF receivers. So basically this is not that much effect that will not that much effect will affect basically. So because I actually told it will, as the frequency increases, its noise is very low. As these radio frequency signals has a very high frequencies from hundreds of kilohertz, so this noise can't be that appreciated, like it can't be much an issue. Next, oscillator stability. So in MTA, that is moving target indicator, radar Doppler process is used to detect moving targets in cluster. So in order to radially detect the Doppler shift, the local oscillator has to be stable. So this can also be used to detect moving targets. So in that moving targets, what we have to do, what we need is this local oscillator should be stable to detect the moving target. That's what here they are meaning. So oscillator stability. So oscillator stability is how stable the local oscillator is. So now phase noise. So phase noise also is one of the noise that can be occurred due to few factors. So instability or phase noise can be caused due to power supply ripple, mechanical or acoustic vibrations from the fans, motors and cooling systems, by vibration of the platform such as aircrafts or ships, and also superior responses and noise from the state itself. Now coming to the types of oscillators. So there are different types of oscillators that are crystal oscillator, frequency multiplier, dielectric resonant oscillator, surface acoustic wave oscillator. Next, YIG means yttrium iron garant, like I think it's a compound, okay, chemical compound, using that that type of oscillator. Next, Kriston oscillator or gun oscillator, high temperature superconducting oscillator, direct digital synthesis. So these are the types. Let's see, okay, what and all, like how it will be. 1 minute. So this is like this is the crystal oscillator, this is a frequency multipliers. Next, this is digital and dielectric resonators. Next, that is surface acoustic wave oscillator, and this is via yttrium iron gas. Next, Klystron oscillator, like high semiconductor, it's like this. Next, direct digital means normal process. So manually we will generate an oscillating signal. So these are the things, different types of oscillators. Now coming to next. So next, duplexers and receivers protectors. So this is one figure, that is balanced duplexer using dual TR tubes and 2 short slot hybrid junctions. So basically a transmit condition and B is receiver condition. Now it is a transmit condition. Now second is the receiver condition. So while transmitting condition, what happens? So when something is transmitted, it will get only, see, nothing will be fed inside of this. So basically it is looking somewhat like a coupler. So but no, it's not. So what happens when this transmitter hits here due to impedance change, and what will happen? It only allows, sorry, see, when something is need to be transmitted, the transmitted signal will be goes and hit the dual TR tube. Due to some impedance difference, what will the entire signal will be reflected back and sent to, and it will be directed towards the antenna, and the same thing happens here also. Now coming to second one is the receiving part. What happens in the receiver? When the antenna is coming to the, and from the antenna, the received signal will be enters this device. So it will goes through this to split it into two signals. One will pass it through over here and the other will be going through here. And actually this dummy load, what will it do? Due to this high impedance, it will go also reflect, it will deviate in the downward direction and will be combined again and sent it to over here. This is the receiver okay, transmitter and the receiver. This is how it will happen. So when something is transmitted, it won't go to the receiver. So when something is coming from the antenna towards the receiver, it won't go to the transmitter. This is how it will work. Now coming to the radar displays, there are several 10 types. So there are types. These are the types of radar displays. One is A scope, B scope, C scope, E scope, PPI display or plane position indicator. Next RH displays or range height indicator, cathode ray tube, CRT display, normal TV, old and STs. Okay, next stroke and rest display, scan converter, flat plane displays, FPD. So let us see in the how they are look in the real life. So now coming to the types of displays, so you can see in the real life they will be looking like a scope, okay, and you can see the B scope, it will somewhat like this, C scope and E scope. This is a plane position indicator display, that is a high radar. Also this is a range high indicator. And CRT is the cathode and normal television type. Okay, it will be looking the same. So if you want, you can see the radar. So it will be like a TV thing to monitor display. Next stroke, and it is somewhat similar to same CRT only. So raster scan means it will scan the lines, each line. It will be like if you see a slow motion, okay, you can have some videos also in YouTube that how like when you film the this normal olden days TV, that is CRT TVs, using the slow-mo cam, you can see each line will be scanned and will be stored, and each line by line it will scan and see the image, entire image will be formed. So let us take this example. Here first line is scanned and there is one dot in that, second line it will scan two dots like that. So it will scan and place the where the position it will highlight only the image pixels in that region. So each line it will scan and display after displaying like after scanning all the lines, one image will come. So after that again next one like that. So next coming to this so what is scan converter? So it will convert what is being scanned, it will convert it to an image like this. Now flat, this is like one more model of the display. So these are the types. So this is recording the radar receiver. Hope you enjoyed. If you didn't subscribe, please subscribe, like, share and comment. Thank you.